fault-tolerant quantum computer, one with maybe millions of qubits all working together, well, it's just an enormous challenge.
It really is one of the biggest engineering hurdles imaginable, actually.
Right, because quantum information is just so unbelievably fragile. So how do you even start building something that complex, that delicate, especially at that kind of scale?
Yeah, it's a huge question. And lots of different groups are trying different things, different types of qubits, different ways to connect them. But getting to millions, that's where the traditional lab approaches start to look, wow, really difficult.
Okay, so that's the setup, the big problem. And that's exactly what we're diving into today. We're looking at a really fascinating approach, one that tries to solve this by bringing together two worlds you might not expect, light and silicon. The idea is to use that massive multi-trillion-dollar semiconductor industry, the folks who make all the computer chips, not just borrowing tools, but really adopting their whole manufacturing way of thinking.
It's a profound shift, yeah.
So our mission today is to unpack how this kind of hybrid system works, how it combines flying qubits with stationary ones to try and get around some of the biggest roadblocks in quantum computing.
It's really where, deep quantum physics meets large-scale industrial engineering. You're designing a system where the strengths of one part, say light, compensate for the weaknesses of the other, like silicon and vice versa. It's a very strategic way to divide the work.
Okay, let's start unpacking that. First foundational piece, the photon. This is our flying qubit, the quantum messenger. So why photons? What makes them so good for moving quantum information around?
Well, photons are pretty amazing as flying qubits. Mainly because they're bosons, which means they naturally interact very, very weakly, both with the environment and with each other.
Okay, weak interaction. What does that give you?
It gives you really long coherence times. They basically hold on to their quantum state for much longer periods compared to matter-based qubits, and they're naturally quite tough, resilient to a lot of the noise that messes up other qubits.
Right.
So they're just ideal for sending quantum information over distance. You can even send them through the optical fibers we already have crisscrossing the planet.
And there's a huge practical plus too, right? Thinking about complexity and cost.
Yeah.
A lot of the photon stuff can work at room temperature.
Absolutely. That's a massive advantage. Not needing ultra-cold refrigerators for every part of the system simplifies things enormously, reduces energy, reduces cost. It's a potential game changer for system design.
So how do you actually encode quantum information onto a single photon?
There are several ways, actually. You can use its polarization, like whether it's oscillating horizontally or vertically or some combination. That's pretty common.
Okay.
Or you could use path encoding. The photon is in a superposition of traveling down, say, path A and path B at the same time, or time bin encoding based on its arrival time, or even frequency encoding using different colors of light. Each has its pros and cons depending on what you're trying to do.
Okay, so we've got these great quantum messengers. They're robust, they travel well. But what about actually doing the computation? Things like linear optical quantum computing, LOQC, or measurement-based quantum computing. What's the catch for photons doing it all themselves?
Yeah, that's where things get tricky for photons alone, because they don't interact strongly. Making two photons influence each other reliably, which you need for those crucial 2-qubit gates, is really hard.
Wow.
LOQC often relies on probabilistic gates. They only work sometimes based on measurement outcomes you have to check afterwards. That's not very efficient if you need lots of gates. MBQC tries a different route, preparing a big entangled state up front, but building that state efficiently is still a challenge.
So the key takeaway here, if I'm getting this, is photons great for carrying the quantum information, but not so great for the heavy lifting processing part because those interactions are iffy.
Precisely. It points towards this strategic division of labor we mentioned. In these hybrid systems, the photons aren't meant to do the bulk computation. Instead, they act as a quantum bus, a high-fidelity interconnect. Their job is to transmit quantum states reliably over distance, maybe between different processing units, and create entanglement between them. They solve that critical long-range connection problem.
Got it. They're the communication network linking the processors.
Exactly, the flying link between stationary processors.
And that brings us perfectly to those stationary processors, the electron spin qubits in silicon. Now, why silicon? What's the big attraction there?
Well, it really boils down to one main thing, leveraging that absolutely enormous multi-trillion-dollar CMOS manufacturing industry.
The chip makers.
The chip makers, they've spent decades perfecting how to build billions, literally billions, of transistors with incredible nanoscale precision on silicon wafers. If we can make our qubits using those same tools, those same processes, that's the clearest path anyone sees to making the millions or billions of qubits we'll eventually need. It's all about scalability.
And silicon itself offers a pretty special environment for qubits too, right? This idea of a semiconductor vacuum.
Yes, that's crucial. Natural silicon has different isotopes, and one of them, silicon-29, has a nuclear spin. That spin acts like a tiny magnet, creating magnetic noise that can mess with your electron spin qubit.
Right, noise is the enemy.
Always. But you can create isotopically enriched silicon that's almost purely silicon-28, which has zero nuclear spin. So you get rid of that magnetic noise source. It creates this incredibly quiet environment for the electron spin.
Yeah, that means
Exceptionally long coherence times. We're talking microseconds, even milliseconds for electron spins, and potentially seconds or even minutes for nuclear spins if you use those instead. That makes silicon incredibly promising for holding quantum information reliably.
Okay, so how do you actually make a qubit in the silicon? I hear about quantum dots and donor spins.
Right, two main types. Quantum dot spin qubits are maybe the most common. You use tiny metal gates, patterned using standard chip-making techniques, very much like the gate in a normal transistor, to create a tiny potential well that traps just a single electron.
Like a tiny cage for one electron.
Exactly. And then you control its spin, maybe using microwave pulses for single qubit rotations. For two qubit gates between neighbors, you use something called the exchange interaction, basically letting the electrons' wave functions overlap slightly.
And donor qubits.
Donor spins are a bit different. You intentionally embed a single impurity atom, like a phosphorus atom, into the silicon crystal lattice. That phosphorus atom has an extra electron, and you can use the spin of that electron, or even the spin of the phosphorus nucleus itself, as your qubit. These can have extremely long coherence times because they're naturally very isolated within the silicon crystal.
So we're designing these quantum devices, but the big question is, can the actual CMOS foundries, the big industrial chip factories, really make these things with the quality we need? What's the progress there?
That's been one of the most exciting developments recently. The answer is increasingly yes. We're seeing reports of high-fidelity qubits being made in commercial, standard 300-millimeter CMOS foundries.
Really, what kind of fidelities are we talking?
Single qubit gate fidelities over 99.9%. And two qubit gate fidelities over 99%. Getting those numbers out of a standard industrial process is, well, it's a monumental achievement.
Wow. Okay, that is seriously impressive.
Yeah.
So this isn't just making tiny lab experiments anymore. What's the bigger picture here? What kind of shift does this represent?
It really validates the whole vision of a quantum system on chip, or SoC. The idea is you don't just make the qubits on the silicon chip, you make the qubits and the classical control electronics needed to operate them all integrated together on the same piece of silicon.
Ah, like how our computer processors have memory controllers and graphics integrated now.
Exactly like that. But for quantum, this helps solve the huge wiring bottleneck problem you see in other quantum approaches, where you need potentially millions of wires going into a fridge to control the qubits.
Right, gets messy fast.
Very messy. Integrating the control electronics close by dramatically reduces signal delays or latency, which is absolutely critical for quantum error correction, where you need fast feedback. It's a shift towards industrial-level integration.
Okay, silicon sounds fantastic then. CMOS, fabrication, long coherence, integrated control. Are there still challenges? What are the downsides or hurdles for silicon qubits?
Oh, absolutely. It's not perfect yet. Two main challenges stand out. First, variability. Even with amazing CMOS precision at the nanoscale, tiny imperfections mean that every quantum dot you make is slightly different from its neighbors.
So they're not identical twins.
Not quite. Each one needs to be individually characterized and tuned up with specific voltages to get it working optimally. Now, imagine doing that for millions or billions of qubits. It's a massive classical computing and calibration challenge.
Okay, that sounds daunting. What's the second challenge?
Connectivity. That exchange interaction we mentioned for two qubit gates, it's very short range. It basically only works between immediately adjacent qubits.
So only neighbors can talk directly.
Right. Making connections between qubits that are far apart on the chip or on completely different chips is really, really difficult with just the silicon qubits themselves.
The light bulb moment. That's where the photons come back in, right?
Yeah.
To solve that connection problem.
Exactly. This is the beauty of the hybrid approach.
Yeah.
You don't need to physically move electrons around over long distances. You use the photons as messengers between distant silicon spin qubits.
Wow.
The photons can mediate entanglement. They can basically link up spin qubits that are far apart, even on different chips, creating a fast, low-noise quantum network. So the silicon handles the dense local processing where connectivity is easy, and the photons handle the long-range communication.
Okay, that makes a lot of sense. So we have our flying qubits, photons, and our stationary qubit, silicon spins. But to make them work together, we need that bridge, that interface between light and silicon. How do we transfer the quantum state? Well, we start with something familiar, like
Yeah.
how does my phone camera work?
Yeah.
That's light hitting silicon, right?
It is, and it's a great starting point to understand the difference. Your phone camera's CMOS sensor is a marvel of classical photon-to-electron conversion. It has tiny microlenses focusing light onto pixels. Each pixel has a photodiode. When photons hit the photodiode, they use the photoelectric effect to generate electrons. The sensor basically counts up how many electrons are generated in each pixel over the exposure time. More electrons means a brighter pixel.
Right, so it's essentially a very sophisticated light meter measuring intensity. What's the crucial thing it doesn't do for quantum?
While it's incredibly efficient at capturing images, that classical sensor fundamentally integrates the light intensity over time, and in doing so, it completely destroys any quantum information the photons were carrying.
It destroys it.
Yep. Things like polarization, or if the photon was in a superposition of states, all that delicate quantum information is lost. It just averages everything out to give you a brightness value. Its job is measuring intensity, not preserving quantum states. You know, what really stands out here is that this amazing bit of engineering in your pocket, your phone camera, is completely useless for quantum processing because it just averages things.
Okay, so if we can't use a regular camera sensor, but we need to detect maybe just a single photon for quantum tasks, like reading out a measurement result, what do we use? We need something much more sensitive.
We absolutely do. For quantum measurements, you often need detectors that can reliably tell you, yes, a single photon arrived, or no, it didn't, and do it with very precise timing. This is where devices like SPEPADES come in single-photon avalanche diodes.
Avalanche diodes.
Yeah.
Sounds dramatic.
They kind of are. They operate in what's called Geiger mode. A single incoming photon gets absorbed and triggers this massive cascade and avalanche of electrons inside the diode. It creates a very easily detectable electrical pulse. Huge internal gain. It's basically a binary detector. It goes click when a photon hits it.
Okay, a single photon clicker. What about CPMs? Silicon photomultipliers.
SiPMs are essentially just arrays of hundreds or even thousands of these SBNs, all wired up together in parallel on a single chip. By having lots of them, they can do more than just say click. They can actually count how many photons arrived at roughly the same time, up to a certain number. That's called photon number resolving, or PNR capability.
Right, so these SPNs and CPNs are vital tools for reading out the results of quantum experiments. Like, maybe after a photon goes through a polarizing filter, the SPN tells you if it came out horizontally or vertically.
Exactly. They are absolutely essential components for the measurement and readout stages.
But, and this feels like a critical but, they still don't do the thing we need for the hybrid connection, right? They detect the photon, but they don't transfer its quantum state into an electron's quantum state coherently.
That's the crucial distinction. Correct. CPEDs and CPMs are detectors. They measure, and in doing so, typically destroy the quantum state. What we need for the hybrid interface is something much more subtle and complex, coherent state transfer.
Quantum transduction.
Quantum transduction, exactly. The goal, the ambition, is to take an arbitrary quantum state of a photon, say, some specific superposition of horizontal and vertical polarization, and faithfully map that exact state onto the spin of a stationary electron, preserving all the delicate amplitudes and phase information. That's the real heart of making this hybrid processor work.
And the key component for that is the semiconductor quantum dot again, maybe a different kind, like indium gallium arsenide.
Yes. Often materials like ingays embedded in gallium arsenide are used for this interface. These quantum dots have specific optical properties that can trap an electron, and crucially, the energy levels involved in absorbing or emitting a photon are linked to the electron's spin state. That link is what makes the transduction possible.
Okay, so how does it work? How do you actually transfer the state? I've heard it involves something like quantum teleportation.
It is very similar in principle to quantum teleportation. Yeah, it's quite clever. Okay, let's try to break it down. First, you need to create an entangled resource pair. Typically, you excite the quantum dot so that it emits a single photon, and the state of that emitted photon, say, its polarization becomes entangled with the spin state of the electron left behind in the dot. This is your herald photon.
So step one, entangle the electron in the dot with a photon it spits out.
Right. Now, you take the photon whose state you actually want to transfer, let's call it the message photon, our flying qubit, and you need to make it interact with that herald photon.
Okay.
Specifically, you perform a joint measurement on both the message photon and the herald photon. This is called a Bell state measurement. It projects these two photons onto one of 4 possible entangled states.
And measuring those two photons, what does that do to the electron way back in the quantum dot?
This is the magic of entanglement. Because the electron was entangled with the herald photon, measuring the herald photon along with the message photon instantly affects the electron's state. Specifically, it projects the electron's spin into a state that's directly related to the original state of the message photon.
Instantly. Wow.
Well, the state collapses instantly, yes, but you don't know exactly what state the electron is in yet. The specific outcome of your Bell state measurement, which of the 4 results you got, tells you how the electron state relates to the original photon state. It might be exactly the same, or it might be flipped or rotated in a specific way.
So you need to know the measurement result.
Precisely. You measure the photons, get 1 of 4 results, and send that result as classical information like over a normal wire back to the quantum dot. Based on that result, you apply a simple, quick correction pulse, like a specific spin flip, to the electron. And boom, after that correction, the electron spin is now in the exact same quantum state as the original message photon was. You've completed the transfer.
That sounds incredibly complex, but also really cool. Has this actually been done in the lab? I think I saw a paper, maybe Hey et al., getting something like 78.5% fidelity.
Yes, exactly. That kind of experiment was a landmark demonstration. Getting 78.5% fidelity is a big deal. It's significantly better than the best you could do classically, which is about 66.7% for this kind of state transfer. So it clearly shows the quantum transfer has happened.
Okay, but here's the catch, right? 78.5% is great for proving the concept, but for fault-tolerant quantum computing, we need fidelities way up in the high 99s, like 99.9% or better.
That's the crucial point, yes. What's fascinating and also challenging is that while 78.5% is scientifically significant, it's nowhere near good enough for building a fault-tolerant machine.
So this interface.
This photon-to-electron transduction interface, despite the progress, is currently seen as one of the noisiest, most error-prone parts of the whole proposed system. It's arguably the critical bottleneck for making this entire hybrid architecture practical. Getting that fidelity way, way up is priority number 1.
Okay, so we have the silicon qubits for processing, the photons for communication, and this tricky low-fidelity interface connecting them. How do you actually structure this whole thing? You mentioned earlier it's modular. Why not just try and cram everything onto one giant chip?
Yeah, trying to build one single massive quantum chip with millions or billions of qubits just runs into too many physical problems. How do you cool it effectively? How do you route all the signals and control wires? How do you get information in and out? It becomes an engineering nightmare. So a modular approach seems much more practical.
Makes sense. Break it down.
Exactly. The idea is you build smaller, manageable quantum modules. Each module would be a silicon chip containing a reasonable number of high-quality spin qubits for doing the local processing. They handle the nearby computations where connections are easy.
Okay, so lots of smaller processing units. How are they linked together?
They're linked by that photonic interconnect we talked about. This could be waveguides directly integrated onto the chips, or maybe connections via optical fibers running between the modules. This photonic network is what turns the collection of small modules into one large distributed quantum processor.
And this structure enables a specific way of computing called fusion-based quantum computing. What's that?
Right. Fusion-based computing is a really neat idea that fits perfectly with this modular, photonically linked architecture. The basic idea is you first create small entangled states locally within each module. For example, entangling a few spin qubits together.
Okay, local entanglement first.
Then you use that photon-electron interface to generate photons that are entangled with certain qubits in these local clusters. You send these photons from different modules over the photonic network to a central measurement station. At that station, you interfere the photons from the different modules and perform measurements on them, similar to the Bell state measurement we discussed for transduction. If you get the right measurement outcome, BASO, it fuses the initially separate entangled states from the different modules together.
So the measurement on the photons actually entangles the qubits in the distant modules.
Yeah.
Even though they never directly interacted.
Exactly. That's the power of it. Successful fusion measurements effectively stitch together the small local entangled states into one massive distributed entangled state, often called a cluster state, that spans across multiple modules. You can then perform computation by doing simple single qubit measurements on this large cluster state.
Wow. So this really changes the nature of the scaling problem, doesn't it?
It absolutely does. The challenge shifts dramatically. Instead of how do we build one impossibly huge, perfect quantum chip, it becomes how do we reliably mass produce many identical, high-quality, smaller quantum modules, and how do we make the photonic links and fusion measurements between them really efficient and high fidelity. The main bottleneck moves away from just making qubits towards the engineering of the interfaces and the network that connects them.
And this brings us right back home to the silicon CMOS advantage, doesn't it? Because if you need to mass produce identical modules,
That's where CMOS shines. The ultimate vision here, sometimes called Quantum 2.0, is incredibly ambitious. It's to fabricate all the necessary components, the silicon spin qubits, the silicon-photonics for the interconnects, the quantum detectors like SPs, and the classical CMOS control electronics all together, integrated on the same chip, using the same mature CMOS manufacturing processes.
a true quantum system on chip.
Precisely. And we can see how each piece fits. The spin qubits, defined by structures very similar to CMOS transistors. The silicon-photonics, that's already a well-established field using CMOS techniques to make waveguides, beam splitters, modulators. The quantum detectors. SPDs and SiPMs are fundamentally semiconductor devices, perfectly suited for CMOS integration. And the classical control. We can even design spiralized cryo-CMOS circuits that work efficiently at the low temperatures needed for the qubits, right alongside them on the chip.
The potential advantages of that level of integration seem enormous.
They really are. First, scalability. CMOS is the only technology we know of that has proven it can scale to billions of components reliably and cost-effectively. Second, latency and power. Putting everything close together dramatically reduces the distance signals have to travel, which is crucial for the fast feedback loops needed in error correction, and it lowers power consumption.
And cost and reproducibility, presumably.
Absolutely. Leveraging the existing multi-trillion-dollar semiconductor industry infrastructure promises much lower costs and higher manufacturing yields compared to building everything with exotic, bespoke techniques.
It really feels like a fundamental shift in perspective, away from pure physics discovery and towards industrial engineering.
It definitely is. The key questions start to sound less like, can we discover a new type of qubit? And more like, can we manufacture 1 million qubits that are almost identical? Or can we integrate the control electronics reliably? Or what yield and uniformity do we need in the manufacturing process to achieve fault tolerance? These are the kinds of questions the semiconductor industry has been successfully tackling for decades.
But it's not all smooth sailing just because we're using CMOS, right?
Yeah.
There's still major challenges. You mentioned decoherence and loss earlier. That fight is still ongoing.
Oh, absolutely. Decoherence, the loss of quantum information, is the persistent enemy in any quantum system. And it shows up in different ways here. For the silicon spin qubits, even in enriched silicon, you still have residual noise sources, like charge fluctuations near the silicon surface or interfaces, and maybe tiny amounts of leftover magnetic noise.
Okay.
For the photonic qubits traveling in the interconnects, their main enemy isn't so much decoherence in the traditional sense, but rather just getting lost. Photons can get absorbed in the waveguide material or scattered out, or the detectors might not be perfectly efficient. Losing a photon usually means the quantum operation it was part of fails completely. It's a catastrophic error.
And then there's the big one we keep coming back to, the interface.
Right. That photon-electron interface is currently a major source of both decoherence and loss. The process of converting the quantum state isn't perfect, leading to fidelity errors, and the efficiency of getting the photon into and out of the quantum dot to interact with the electron spin is often quite low, leading to losses. That 79% fidelity number reflects both issues. It's the weakest link.
So what are people doing to fight back against all these error sources? What are the main mitigation strategies?
There's a whole toolbox. For the spin qubits, besides using that ultra-pure silicon-28, researchers work on improving the material quality, especially at the interfaces where charges can get trapped. They also use sophisticated control techniques called dynamical decoupling, essentially applying carefully timed sequences of pulses to the qubit to cancel out the effects of slow noise sources, and sometimes operating the qubits at specific sweet spots where they're naturally less sensitive to certain types of noise.
Okay, that's for the spins. What about getting the photons in and out more reliably at the interface?
That's a huge area of research. One key technique is called cavity quantum electrodynamics, or cavity QED. The idea is to embed the quantum dot inside a tiny optical microcavity, basically, perfectly engineered nanoscale mirrors.
My mirrors.
This cavity traps the light, forcing the photon emitted by the dot to bounce back and forth many times. This enhances the interaction between the electron spin and the light field, something called the Purcell effect. It can dramatically boost the probability that the dot emits its photon into the specific channel you want, like into your optical waveguide, increasing the collection efficiency from maybe just a few percent in free space to potentially over 90%.
Wow. Okay, so trapping the light helps funnel it out efficiently. What else?
Another crucial thing is making sure the photons involved in interference, like in those fusion measurements, are perfectly identical or indistinguishable. If they have slightly different frequencies, for example, they won't interfere properly and the fusion will fail.
Right.
So researchers use techniques like the Stark effect. By applying precise electric fields across the quantum dot, they can fine-tune its exact emission frequency, effectively tuning the photons to be perfectly identical.
Okay, so lots of clever tricks. But this brings up a really important point. How do all these error rates and efficiencies combine? You've got potential errors in the spin qubits, photons getting lost, and this imperfect interface. How does it add up for the whole system?
That's the system-level error budget question, and it's critical. The overall success probability or fidelity of any operation that spans the hybrid system is essentially limited by the weakest link in the chain.
Which is currently the interface.
Let's imagine, just as an example, that your spin qubits are almost perfect, say 99.99% fidelity. But maybe the combined probability of successfully generating a photon from the dot, transmitting it without loss, and transducing its state at the other end is only, say, 10%. And let's say the subsequent fusion measurement works with 90% fidelity.
Okay.
The overall probability of successfully entangling two remote qubits using this process would be roughly 0.99999 for the qubits, times 0.10 for the photon channel, times 0.90 for the fusion, which is less than 9%.
Oof. Less than 9% success per attempt.
Exactly. And you might need thousands or millions of such operations. It just highlights how devastating even one bottleneck with low success probability can be for the entire system's performance. We need massive improvements, particularly in that photon generation, transmission, and transduction efficiency and fidelity orders of magnitude, really.
That's a really stark picture of the challenge. So even with CMOS manufacturing helping with the scale, getting to true fault tolerance seems like it needs more breakthroughs. What about that tuning problem you mentioned earlier? Millions of slightly different qubits.
Yes, that remains a huge challenge, even if CMOS can fabricate the devices. How do you efficiently characterize and calibrate potentially millions or billions of individual qubits, each needing slightly different control parameters? Doing it manually is impossible. The only feasible path seems to be through highly sophisticated automation, probably involving machine learning and AI algorithms, to develop automated tuning procedures that can run quickly and efficiently across the whole processor.
And the photonic network itself must have limits too.
It does. As you scale up to millions of qubits needing to communicate, the demands on the photonic interconnect, the number of channels needed, the bandwidth, the switching speeds, minimizing photon loss across the network become formidable engineering challenges in their own right.
Okay, so the ultimate goal through all of this is fault tolerance, using quantum error correction, QEC. You said that needs very low physical error rates.
That's the non-negotiable requirement. QEC codes work by encoding the information of one logical qubit across many physical qubits. This redundancy allows them to detect and correct errors, but only if the error rate of the underlying physical qubits and operations is already below a certain critical value, known as the error threshold.
And that threshold is typically around.
But for many common codes, it's roughly around 1% per operation. This means the fidelity of your physical gate's single qubit, two qubit measurement, and crucially, that photon-electron transduction needs to be significantly above 99%.
And we're currently at maybe 79% for the transduction.
Exactly. Orders of magnitude away. That 79% transduction fidelity is the single biggest roadblock preventing this architecture from reaching the fault tolerance threshold today.
So looking forward, what are the key strategic research directions? Where do efforts need to be focused to bridge this huge gap?
It's really across the board. We definitely need continued breakthroughs in fundamental materials, science and fabrication, trying to make quantum dots that are much more uniform and have better optical properties right from the start.
Okay, better materials.
Then there's device engineering and integration, Things like designing even better optical cavities, maybe moving towards monolithic integration, where the quantum dot is grown directly within a perfectly designed photonic crystal cavity on the silicon chip itself to maximize that light extraction efficiency and coherence.
Improving the hardware interface.
Right. We also need advances in quantum protocol development. Are there cleverer ways to perform the transduction or the fusion measurements that are naturally more robust to photon loss or other dominant errors? Maybe protocols that require fewer photons or less precise timing?
Smarter software, essentially.
And related to that, we need more work on tailored error correction theory. Since this hybrid architecture has very specific types of errors that are more likely than others, like photon loss being much more common than a spin flip error, perhaps we can design QEC codes that are specifically optimized to handle this bias noise more efficiently than standard codes.
Makes sense. Target the error correction to the specific problems.
Yeah. And underpinning all of this is the need for what we call co-design.
Co-design.
It means you can't just have the material scientists working in one lab, the device engineers in another, and the quantum algorithm theorists in a third. Progress really requires a deeply integrated parallel effort where all these groups, plus the CMOS engineers, are constantly talking to each other, understanding the constraints and opportunities at each level, and optimizing the whole system from the atoms up to the algorithms together. It has to be a virtuous cycle.
Okay, so let's try and wrap up this deep dive. The core idea we've explored is this hybrid silicon-photonic quantum processor. It's a really compelling vision, trying to unite the strengths of silicon for processing and CMOS for scaling with the strengths of photons for long-distance communication.
Exactly. The modular design, linked by light, offers a potentially plausible path around the scaling and connectivity walls that other approaches might hit. It shifts the problem towards engineering manufacturable modules and efficient photonic links.
And leveraging that incredible CMOS infrastructure is obviously a huge potential advantage, maybe the clearest path we see towards the millions of qubits needed for fault tolerance. It turns it into an industrial engineering challenge in many ways.
It does provide a tangible roadmap, and the progress in fabricating high-fidelity qubits and CMOS foundries is genuinely exciting. It shows the basic premise is sound.
However, we have to be realistic. This is definitely not something just around the corner. That photon-electron interface, the quantum transduction step, remains the Achilles heel.
Absolutely. It's the single most critical and pressing task, as you said. The current fidelity and efficiency are just nowhere near good enough for fault tolerance. Still orders of magnitude away from that crucial threshold. That interface is the make-or-break point right now.
The technical hurdles there are still immense. Improving that fidelity while maintaining efficiency is where a huge amount of innovation is needed.
Without solving that interface problem, the whole architecture, however elegant, won't reach its potential for fault-tolerant quantum computing.
So thinking about the bigger picture from our dive today, it really seems like the future for this specific, very promising hybrid approach hinges maybe less on discovering brand new quantum physics and much more on mastering these incredibly difficult but perhaps more conventional industrial scale engineering and integration challenges.
That's a fair assessment for this stage, yes.
The central question seems to be shifting from can we build one perfect qubit towards can we manufacture millions of nearly identical qubits with integrated controls and then network them perfectly using light. So here's something to think about. What does this shift towards an engineering and manufacturing problem mean for the timeline of quantum computing? And maybe even for who will be driving the next big breakthroughs? Is it still academic labs or increasingly large industrial players?